Welcome to our next set of notes for mathematical reasoning. We're in section 6b. So last section we talked about ways to measure center. We talked about mean, median, mode, and how we can use those to figure out kind of what the center of our data is. Talked a little bit about shapes of data, how we can have unimodal, bimodal data, symmetric data where things are spread out nice and evenly. Today we're going to focus primarily on variation, the spread of your data. It's nice to know where the center is, but you also need to know about the spread of the data. Those are kind of the two big things to know when you're studying data. So here I have two sets of data. These are from two banks. They track their wait times for customers. They both have 7.2 minutes for their mean and their median. So the measure for center, they both give 7.2. So their average, we could say, would be 17.2 minutes. One of the banks actually had much lower customer ratings than the other, even though their average wait times are about the same. So looking at these, we can think about why. So you say big bank, there are some people waiting close to 7.2 minutes, a little bit more, a little bit less. There are people waiting much less. You'd think maybe you'd give them better reviews, but there's also people waiting a lot more. Their wait times are all over the place, everywhere from 4 minutes to 11 minutes. There's quite a difference. Versus best bank, everybody comes in and gets pretty close to 7.2 minutes. The smallest is 6.6, the biggest 7.8. That's only half a minute more, and this is just about a minute less. So they're all pretty close at the same time. So in this case, Big Bank had lower ratings because some people are sitting there watching two other customers get started in the time it takes for them to get to their turn, because they're waiting 11 minutes, other people are waiting 4 or 5 minutes. So Big Bank had the lower ratings because it had so much more variation. There was more spread in the data. So even though they did a good job getting their wait times to 7.2 minutes, just like Best Bank, Big Bank didn't do a great job with their variation. I think this might be a situation where Big Bank has your typical 2 or 3 tellers, and you just pick a line and get in that line. And if you get in the right line, it's great, but if you get in the wrong line, you have to wait forever. Whereas Best Bank maybe does that practice where they have one line and then like 3 tellers, and the teller helps whoever's next in the line. So there's, the line's always moving, and no one's stuck being the one person that has to wait 11 minutes versus everybody else getting to go in, 7 minutes or less. So they have the same center, but they differ greatly in variation. This is a chart, this is a histogram to show kind of the difference. So Big Bank, you can see it's spread all out over the place. Everything from 11 down to 4. Best Bank, everything's within that 7 to 8 range. They just don't have nearly as much spread. They both have the same average, so 7.2 would be about the average here. You can see that'd be in the middle of both sets of data, but they have much different spread. So we need to measure spread. We need to measure variation. There are times when that's going to be even more important than measuring, the mean or the average. Sometimes you just want to know that spread, or sometimes you'll use both. There's actually a lot of cases where we need both the spread and the measure of center to really understand the data set. Now, the simplest, easiest way to measure spread is the range. Range is just the highest value minus the lowest. It's the max minus the min. That's all range is. You just take the biggest number, the difference between the highest number and the lowest, and find that difference. Just range is just max minus min. I didn't write on the formula sheet, so you do need to know this for the test, but it's just max minus min, top minus bottom. That's all it is. So here I have a teacher trying to figure out how their classes are doing. The class is doing with 2 different quizzes. And so quiz 1, we just look and see that 10 is the highest and 2 is about the lowest. So for quiz 1, you do 10 minus 2, and you see that they have an 8-point range from the highest quiz to the lowest quiz. Quiz 2, we can see here that 15 is the highest, and this time 3 is the lowest. So we just take 15, we subtract 3, and we see that they have a 12-point range. So now I can say there's a bigger spread in the scores for quiz 2 than there is for quiz 1. So if I'm looking at a test that has more of a range of values, I do quiz 2. If I want a quiz that the values are more closer together, there's not quite so much spread, I do quiz 1. That's what I would look at. I could say, okay, what do I want, more spread or less spread? That depends on the situation. But yeah, I can see that there's more spread with quiz 2 than there's with quiz 1. Here we looked at prices at 2 different stores for movies. What are the ranges of prices? Which set is more varied? So look at this first set. I see there is a movie that costs $21 was the high price. We have 15 as the low price. So for store one, we would just do 21 minus 15. That's all it is. It's just subtracting top minus bottom. And we see there's a 6-point range difference. Store two, I think they're mostly 18s and 16s. There's like the 18 is the high price, but there is a 10 here. So 18 minus 10 tells us this actually has the higher range because it has an $8 difference from the top to the bottom. Now, if I ask you which one's more varied, and you say, well, store two is more varied because there's $8 difference versus 6, I might say, but look, almost all the videos at store two are either $18 or $16. There's really not that much spread in the data. If I graph this as a chart, there'd be a big column at 16, a big column at 18, and then there would be one value at 10. And this is what a typical outlier type position. We kind of saw this outlier last time with the median mode, saw how outliers can disturb means. Well, outliers also can really mess up range. Since range only depends on two values, the top value and the bottom value, if either one of those is an outlier, so since range depends on just the top and bottom, if either one of those is an outlier, it can be really messed up by that outlier. You know, here that's what happened. This one outlier that's so different than everything else, this 10, it totally destroyed this range. If we do it without the outlier, the range for this set of data is just going to be doing 18 minus 16, because the top is 18, the bottom is 16, not an outlier. And so then the range is only $2. And you can see that, well, really, it's just that outlier, because otherwise, store two doesn't have much range in their prices. Almost all their movies are about the same price. It just had one clearance movie for $10. So range, although it's a quick and easy way to talk about spread, it's not a very useful way in real life. Your statisticians wouldn't use it very often because of the outliers. It would mess up a lot of data, because there's a lot of data where you'll have like one or two outliers, and then that will be messed up quite a bit by just that one outlier will destroy range. So instead, we use other measures. One of those other measures are quartiles in the 5-number summary. So instead of just using one number to measure the spread, go from the top to the bottom, the second option is to use a set of numbers. So we're going to use multiple numbers. That way, if we do have an outlier, this isn't going to be disturbed quite so badly. So we're going to take and we're going to chunk the data into 4 equal pieces. So if you think of the data like a loaf of bread and you want to cut it up into 4 equal-sized pieces for this loaf, and it's not pre-cut loaf, then you need to make 3 cuts. What you do is you cut it once in the middle, so you get 2 equal halves, and then cut each one of those halves in half, and then you'll have quarters. We call these quartiles in statistics, and we have the 3 cuts to make. The middle quartile, which is really just the median of the data set, we're just cutting in half. The middle quartile, the median, is the value where you put that, you take that number in the middle, and you'll have half the data above and half the data below. The lower quartile, well, now this is cutting the bottom half, the lower half of the data, in half. So the lower quartile, it's going to be the median of the lower half. And then the upper quartile is doing the same thing for the upper half. So the upper quartile is the median of the upper half. These are also called first, second, and third quartiles, going from least to greatest. The first would be the low quartile, second would be the middle, and third would be the upper quartile. Note, when you're trying to find the upper quartiles, we don't include the median. So if the median is one of the numbers in your data set, you're going to ignore it when you're doing upper and lower quartile. If the median happens to be outside of your data set, it's not one of your numbers, because sometimes you'll end up with 2 numbers in the middle. You find the median, so you have to find the point like halfway between 2 numbers. Then it's not part of your data, and reason you wouldn't use it anyways. So just be careful about that. Make sure you always don't use the median when you're calculating the lower and upper quartiles. So we'll go through a couple examples. And again, this is just a way to kind of look at the data. By getting these numbers, these quartiles, you can kind of see the spread of the data by looking at how far apart these different quartiles are. So for example, for Big Bank, we want to find the mean of the middle quartile, the upper and lower quartile. So we'll do the whole cover-up method like we did for finding median before. We just cover up until we find the middle number. So this number right here is the median, or the middle quartile, median. And because we actually have the number somewhere to is the middle, it's our median, we're not going to use it. We're looking for the lower quartile and the upper quartile. So if we're doing the lower quartile, we're going to ignore the median. We're just going to look at numbers below, and we're going to do the same cover-up method. And here we'd see that 5.6 is the lower quartile. And then we do the same thing. We cover up the median, do the upper half, do our cover-up, and we see that 8.5 is the upper quartile. So now we've made 3 little cuts, picked out 3 numbers in our data set, and we've chunked our data into 4 equal pieces. You'll see the part below the lower quartile, there's 2 values. Between the lower and upper median, there's 2. Between the median and the upper, there's 2. And past the upper, there's 2. So we've got 4 equal size pieces. And this is just an example of a small set of data. But you could do the same thing if you have a data set with 100 or 1,000 numbers. You find these 3 quartiles, and now you've chunked it into 4 equal size. We'll have the same number of values. And the spread of these numbers, how far apart they are, will show you a lot about how spread out your data is. Let's do the same thing with best bank. And we saw last time best bank has a lot less spreads. We should see that in its quartiles. So again, we'll cover up. We already know that the median for these 2 should be 7.2, as we said on the previous page. So 7.2 is the middle quartile. It is the median. Right? The median is the middle quartile. It's just the middle number. And that's what you're trying to find. We're trying the middle quartile. You're trying to find the middle, the median. And then we cover that up and do the middle of the bottom, 6.7. And we cover it up and do the middle of the top, that's 7.7. So that's our lower quartile and our upper quartile. So here we had 5.6, 7.2, 8.5. Down here we have 6.7, 7.2, 7.7. You can see here the numbers are a lot closer together than they were up here. We went all the way from 5s to 8s. Here we're just from 6 to 7. Not much of a change, only one difference between 6.7 and 7.7. And that's how we use quartiles to kind of think about the spread of the data. So quartiles, even though they're just kind of like quarters, they were just chunking the 4 quarters by cutting out these 2 numbers. It's still a nice between the 2 data sets and say, okay, how much difference is there between? Now we usually actually add 2 more values. That's why we said 5-number summary instead of 3-number summary. To get a really complete picture of the data, we actually add 2 more values. We add the lowest value and the highest value. So the 5-number summary, you should know this for the test. The 5-number summary is the min, the lower quartile, the median, which is the middle quartile, the upper quartile, and the max. Now we have those 3 middle numbers that chunk into 4 equal sections, and then we just have the bottom and the top. The lowest and the highest. And that's what we use to get a good picture of the whole data set. Not just find the middle values, we're getting everything. So here I have eruption times for Old Faithful Geyser in Yellowstone National Park. I'm going to give the 5-number summary. Now we got to be careful here. Notice it's not in order. I always get students that try and do this and they don't have an order. You got to be careful. You got to make sure that everything is in order before you start trying to find the min, the max, and all that kind of stuff. First thing I'm going to do here is go to rewrite this in order. So 65, I think, is the lowest. What's next? We've got an 87, so there's a 180. I think 90's next. And then 92. I've got 2 of those, so 1 more 92. Got 93. Got 94. Got 95. Another 95, 96, 98, and 98. Okay, so now we have it all written in order. Now we can figure out what our middle number is. Again, there's like other ways to do this whole find the middle, but I think the cover method is fine for us. Here I have 2 in the middle. And so if I'm doing this right, I can look and see that there's 5 numbers below and 5 numbers above. It tells me that this is the middle, these 2 numbers in the middle. So the median is actually halfway between those 2, which is 93.5. If you add these up, divide by 2, you get 93.5. That is your middle quartile or your median. When I go to find the upper and lower quartiles, I don't use this number because we never use the median. So it's not part of my set, right? And here I do use the 93 with the bottom half because medians in the middle between those two. So it's, I'm not using this median, but there is still 93 as part of your data set, 94 as part of your data set. So when I go to find the middle, the lower quartile, I would use 93 with that set. So I'm going to cover up 93 to, I actually end up with two middle numbers over here as well. So I have to find halfway between 90 and 92, which is 91. And that's going to be my lower quartile. And do the same thing with the top half. Now I'm going to look at 94 and up because 93.5 is my middle, so I'm going to just do numbers above that. Cover up, and I get two numbers in the middle here. So it's 95 and 96 are in the middle. So then the upper quartile is going to be 95.5. Again, if you add these up, divide by 2, you get 95.5. That's the upper quartile. It's just finding the median of the middle, the median, and then find the median of the bottom half and the median of the top half. That's what we're doing. These are our quartiles, but we also need the max, which is 98, and the min, which is 65. And this is a 5-number summary. So the 5-number summary in this case would be 65, 91, 93.5, 95.5, and 98. It's all about medians and the max and the min. Now, all these quartiles are really medians, right? Because you're doing the median of the middle, but then you're doing the median of the bottom half, median of the top half, and then you're just doing your max and your min. And that's the 5-number summary. So this is a set of 5 data values. Now, if I take this and compare it with a different data set, I can see which one's more spread. I look at the difference between the top and the bottom numbers. I might look at the middles. A lot of times it's nice to look at kind of the middle part of the data because you might get your extreme values on the end. Like 65 is probably an outlier. Sometimes people, when they're looking at these, will look mostly at the middle 3 numbers, like quartiles. But the max and min are nice to have there as well because it tells you what the highest and lowest data value is. And that's the 5-number summary. Now, one thing we do with this 5-number summary is we graph it because it is a nice way to show things, but it's nice to be able to visualize. So a lot of people use a 5-number summary to draw what we call a box plot, or you might have heard it called a box and whisker plot. This is probably something you did in school in the past as a box and whisker plot. A lot of times we teach these in middle school or grade school. So a box and whisker plot, it is a 5-number summary drawn on a number line. So it just graphs the spread of your data. So here we have Best Bank and Big Bank again, the same ones. And again, Best Bank, you can see there's a lot less spread. Their 5-number summary goes from 6.6 to 7.8. And then their Big Bank, their 5-number summary is a lot bigger. It goes from 4.1 to 11.0. So with a 5-number summary, you're going to have a line for all 5 points of that 5-number summary. So you have your min, your lower quartile, your median, your upper quartile, and your max. That's what the 5 numbers are. We're going to draw a line that connects all of them. So there's going to be a line right through the middle that connects all the way from your min to max. And we're going to box the quartiles. So just the lower, middle, and upper quartile are going to get a box around them. Now, the reason we design it like this is because, remember, the 5-number summary, we're chunking the data into 4 equal sections. So even though this piece is shorter than this piece, there are the same number of data values in this set as there is in this set. And so the wider the line is, the more you know that part is spread out versus the other parts. Or here, this whole thing is more spread out than this thing. Because again, these are the same size data sets, but these ones are so compact that there's the same amount of data here in this little tiny piece as there is in this whole piece right here. So the size of the piece is showing you the spread of the data because we know that each part is equal size. And the reason why we box the middle part is because the middle part is going to have 2 pieces. It's going to have 50% of your data. That's the middle 50%, and that's the part a lot of people like to look at because, again, the ends are considered kind of the more extreme values. We use this a lot in real life. If you're looking at, example I saw a lot in my business statistics class that I taught once was plane flights. If you look at plane flights and you think about, the weight that the planes can handle and passengers and all that, and that's something the pilots have to be aware of, and the plane manufacturers and all that. They usually go by what's the typical? And the typical people are going to be in that middle range of the middle 50%. The people on the ends are going to be kind of the more extreme people. And they'll have to account for those more extreme people. They check, weights and stuff like that. But they kind of build stuff mostly designed for the middle 50% because that's the most common, most typical. The extreme values at the end, they're not going to expect as much. If you do standardized testing, most, 50% of people are going to be in that middle range, between the quartiles. There's only going to be 50% on these 2 extreme ends. And so those are kind of less common. Sometimes you'll look at just the extreme ends. Maybe you want to know what the extreme values are versus the middle. You can do that here. Or you might want to look at the upper half of the data. So that'd be like everything above the median, or the lower half is everything below the median. So the box plot gives you a nice visual way to think about the data set and see the spread of the data set. Now, how do we make a box whisker plot? Because you should be ready to do this. On the homework, you don't have to draw them yourself so much, just pick out the right one, but be ready to draw this for the test. So to draw a box whisker plot, first you need a number line. Number line should be big enough that it fits all your data. So you see here they went from 0 to 12 because the biggest number they had was 11, so it fits all their data. So draw a number line that spans all your data. Draw vertical lines at the 5-number summary. So at each point in the 5-number summary, you're going to draw a vertical line. Draw a line between the min and the max, connects the whole thing, and then draw the box between the lower and upper quartiles. The box will go all the way around from lower, middle, upper, box that whole middle section. You don't want to box around the whole thing. And sometimes I think people see box plot and they just draw one giant box, but it shouldn't be just one giant box. It should just be a box around the middle, 50% of the data, and then 2 whiskers. That's why in grade school we called it a box or whisker plot. There's a box in the middle and then these 2 little whiskers going up to the ends. So let's draw a 5-number summary for this set of data right here. This is the list of times for Beethoven's 9 symphonies. You can make a box and whisker plot. Before you can make the box and whisker plot, you need the 5-number summary. So using these times, you got to get that. Well, first off, they're not in order. So before you can do anything else, I got to go back and put them in order again. That's a lot of times when you're doing median and 5-number summary, you have to do a lot of putting stuff in order. 2.8, get 3.0, 3.3, I almost did 3.6, but it's 3.3 next. Then 3.6, 3.8, 4.0, 5.0, and 7.0. Okay, so now we got the times listed. We need to find the median. So we're going to find the middle number. So covering up, I'm just going until I find the middle. So the 3.6 is the middle number in this data set. Remember that we don't use that when we're finding the lower and upper quartiles. So we ignore 3.6 and just do stuff below. So in this case, it's going to be halfway between 2.8 and 3.0, which makes it 2.9 because that's halfway between. 3.6 isn't used for the top set, so I'm going to just go like this and say it's going to be halfway between 4.0 and 5.0, which is going to be 4.5. That's halfway between those. Don't forget the top value and the bottom value. So now I've got my middle number, middle of the bottom half, middle of the top half, and then the top and the bottom values. My max and the min. This was the middle quartile, the lower quartile, and the upper quartile. If you draw a box or whisker plot on the test, you should make sure you're definitely labeling all your values. So like right here, I just labeled them so they're kind of clear. Make it clear what you're using. Now to do this, to draw this, I'm going to go down here. I'm going to draw at each one of these numbers a vertical line. So at 2.0, I have a 9 there for the min. At 2.9, which is not quite 3, so I'm going to have one there. At 3.6, it's a little bit more than 3.5, so I'm going to put on a little bit to the past 3.5. At 4.5, so it should be right between 4 and 5, and at 7. Now you have a middle line that goes through all those, so I'm just connecting them all right through the middle. And then we box the quartiles, so from 2.9 to 4.5, so 2.9 to 4.5, that's our box. There's not a box on the ends because those are the whiskers. So we have our min, the lower quartile, the median or the middle quartile, the upper quartile, and the max. And by drawing this box, now I can see that there's a lot more spread in the top 25% of the data. There's a lot more spread here at the end than there is anywhere else. In fact, probably would maybe think that maybe that 7.0 is a outlier. That outlier might be just, kind of really distorting the spread on this side because the previous value is 5, so it would be actually down there. And you see there's not a whole lot of variation except for we have that 1.7. So again, make sure you label. If you draw a plot like this, for the test or whatever, you should be labeling your values. Either, here I could have just said, well, I got these all labeled up here, so you know what these are, 2.0 and 2.9. But, it's good to make sure it's clear. I've had people in the past where they drew a box and whisker plot, and they didn't tell me what the numbers they used were, so I didn't know what these values were supposed to be, and sometimes they were off. And so you should definitely label, either label like this I did, where I have the quartiles and the min-max labeled, and so you know what's going down here, or the numbers themselves written down. That'd be a good way to draw it. So there's not a whole lot of homework questions about this, but still be ready for it. There's a few homework questions towards the end where they're going to have you draw this box of whisker plots. And they're not too terrible. You just have to find the medians, and then that's getting you to that 5-number summary. Okay, now the problem with 5-number summary is one, graphing is kind of a bit of work. You saw we had to do all the steps to graph it. Also, it doesn't give you just one number to talk about the spread of the data. Now you have to use 5 numbers. And it's hard to compare 5 numbers at once or to keep 5 numbers in mind. So it'd be nice if we just had one number that measures the spread that wasn't quite so susceptible to outliers. So that's what we're going to do last. We're going to come up with one more way to measure spread, and it's probably the most commonly used, at least in the introductory level statistics. You get up into higher level statistics and start using other measures. But in introductory statistics, the most commonly used measure for spread is standard deviation. So what in the world is standard deviation? Standard deviation is a way to average the spread of the data from the mean. So we're actually, to calculate standard deviation, we're going to find the mean first. So use the mean to find standard deviation. And then we're going to find the deviations. Deviation is how far each data point, each value, is from the mean. So you're finding the distance from the mean. So you take all those distances from the mean, the deviations, and you average them. So standard deviation is an average of the deviations. That's what it is. Now it's going to be a little weird to calculate the average, so I'm going to show you how to do it. And it's a bit of a process, so I'll go through it. We'll do it a couple times to kind of show you the process. So down here, this is the first time they actually started the process for us. So the first thing they did is they figured out the mean. So before we do anything else, just note that the mean and this is 2 problems, so I'll do the big bank first. The mean is 7.2. We said this is that same bank information we had at the beginning. We knew that the mean is 7.2. Then they had to find the deviations. So to find the deviations, they took each data value and subtracted the mean. So we took, the time 4.1, we subtract 7.2, you got a negative. 5.2, subtract 7.2, you get negative 2. 5.6, subtract negative 7.2. Eventually, when you get above 7.2, you'll get some positive values like 0.5, 0.5, 1.3. And those are the deviations. Now, the problem right now is you went and added all these deviations up. You got positives and negatives, and you actually end up with 0 because there's just as many positives as there are negatives, and they would balance out. And if I'm trying to find, a measure for the spread, I don't want to use 0, especially if that's what the answer is for every single problem, because that's not really going to help me measure spread. So we have to make them positive. Now, you could just take these numbers and make them positive. Just take negative 3.1, make them positive 3.1, and that is actually a type of deviation, but it's not a standard deviation. Standard deviation is, the really fancy PhD statisticians figured out that there's a better way to do it than just making them positive, and that is to square them. Because when you take a number and you square it, it becomes a positive, but it also takes the numbers that are really extreme, numbers that are really far from the mean, and makes them even bigger, and then account for more. So like this negative 3.1 was already pretty far from the mean because it was negative 3 away, but now squaring it turned into 9.6. And doing that makes for a better measure of deviation, of variation. So we're going to do that next. We're going to take every number and we're going to square them. When you're squaring them, you should always get positives. That's the whole point of squaring them, is to make them all positive. Small numbers, like 0.5, they're not going to get very different, just 0.25. In fact, that one should get smaller. So they're not going to be very big, but you're going to square all of them. Get this deviation squared, so that's the next step. Once you have the deviation squared, now to find the average, you add them all up and divide by how many there are. So the next thing to do is to sum them. So we're going to add them all up, and we get 38.46. So we're most of the way there. Big bank, we've found the deviations by subtracting the mean. We squared the deviations to make them positive. We added them all up. Now we have one thing left to do. We actually have to divide, but here's tricky. We actually divide by n minus 1. Remember, n is your sample size. So that's how many times you checked, how many times you looked at. So here I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. So I would divide, but instead of dividing by 11, you actually divide by 10. Again, don't ask me exactly why. This is one of those things the PhD mathematicians figured out, that this is just a better way to do it. So instead of dividing by 11, we're going to do 11 minus 1. We're actually going to divide by 10. So there's 38.46. We're going to divide that by 10. We're not quite done. We got 3.846. There's one last step we have to do. We did all this squaring to kind of get these squared deviations to get them positive. Well, we have to undo that squaring. So the last step we actually have to take, and we have to square root that number to undo all that squaring. So you're going to have to use the square root button on your calculator. Here I'm just showing you with the TI-84, the square root button. second, and then there's this little x squared button down here. There you go, x squared, and a little square root symbol, and that gives you the square root there. And you can type in your 3.846. Oops, we got too many sixes in there. 3.846. And you square root that, and that's your final measure of reduced standard deviation. So standard deviation is 1.961. My math app will tell you how many spots to round to when you're doing that. So you find the deviations, you're subtracting the mean to do that, square the deviations to make them positive, add them all up, and divide by 1 less than the number of values. Then the last thing to do is square root to get your final answer. So your standard deviation, that's standard deviation. And it is the average of all the deviations. Again, deviations are the difference between the numbers and the mean. You're subtracting to find out how far apart they are. It's always the value minus the mean. Let's do the same thing for best bank. So best bank, same thing. We want to find their standard deviation. So again, they started off and they did some of the work for us. The mean is still 7.2, so using that 7.2 mean. They first found the deviations, and you subtracted each value minus the mean. These numbers are not very big because they're all pretty close to the mean, so that's why these are going to be pretty small. Some still are negative, some still are positive. If you add all these up, you would get 0. So then we square them before we add. So we square them to make them all positive, so now they're all positive numbers. And we add them up. So the sum, this time, is actually only 1.98. You can see that's already a lot smaller than that 38 we had. Now, to finish this off, we have to take that sum, and we have to divide it by how many values are. There's still 11 here. So I'm going to do that 1.98 divided by 10, because remember that n is 11 and n minus 1 is 10. Always divided by 1 less than the number of values. So it's not quite the same as average, we did with like mean, where you add up and divide by exactly how many values are. When you're doing standard deviation, it's always 1 less. And then divide that, you get 0.198. And then the last thing to do is do the square root, because you have to undo that square we had up here. So square root that 0.198, and that'll give us our final answer. So what's the square root? Actually, I should just do another calculator so I can show you my TI-30 if that's what you're using. So you have TI-30. It does square roots just as well. So TI-30, you just have a square root button. So there's my square root right here. So see square root. So I would type in second and then type the x squared by mix the square root because I hit second first. You got 0.198. Hit enter. There you go. You got 0.445. I did 3 decimal places each time, but my math app will tell you if they want 2, 3. I have it on the instructions on the test as well. And that's standard deviation. Now we'll go through and we'll do it a couple more times for practice, just so you can get an idea. It's a process, and you kind of have to have the process mostly memorized, know what the process is. And the process is, first you have to find the mean. Then using the mean, you subtract to get the deviations. Square the deviations. Add to get a total. Divide by 1 less than the count, sample size. How many values did you have? And we'll take the 1 away. That's what you divide by. And then square root that answer to get your final answer. So our square rooting is always the last step. Okay, that's where we're going to finish it off. So we're going to do this a couple more times, and we'll be done with this section. So this section was all about finding ways to measure variation, and standard deviation is just a really good way to do that. It's a really good way to measure variation. This is the process. This is kind of similar to the formula on the formula sheet. You'll see the formula on the formula sheet if you look at the formula on D2L or my math lab. Kind of similar to this. It's one of those formulas where I feel like it's actually a lot less useful than students think it's going to be, because it's a little complicated to look at. There's a lot of stuff going on. Basically, it tells you that you need to remember this whole process. It's nice. I keep it there. I put it there mostly as a way to kind of jog memory. If you're sitting there going, well, what are all the things I need to do? Well, you need to square root. Well, there's a square root on there. You need to divide. There's division. You need to use n minus 1. Don't forget to subtract 1. That's there. It says sum of or add up. And, oh, yeah, we have to add up all the values. Don't forget to square the values. So how to think that says square. And deviations, don't forget the deviations are the values minus the mean. So everything's in the formula, but you need to know the process. I get students that walk into the test all the time that didn't really learn the process of finding standard deviation. I don't know how, because it's in the homework a bunch. So you should do it enough times. You should kind of get it down and know what to do. But I think that happens, and then students really, struggle with it on the test. So we'll do it a few more times. Again, this is the process. First, you have to find the mean. You can't find the standard deviation without the mean. I find the deviations. Again, that's subtracting each value minus the mean. Square the deviations. Once you've got all the deviations squared, you have a total. And then once you have that total, divide it by the total by n minus 1. So divide by n minus 1. And then the last step is always to square root. So you have to square root that quotient, which is the answer to the division problem. Square root that at the end. So we'll do that. So first thing we got to do here is need to find the mean for this set. Remember, the mean is always the sum over the number of the values. Here I have 1, 2, 3, 4, 5. I did a small set, so we didn't have to take forever. I'll be nice on the test. I'm not going to give you a huge set of numbers because standard deviation gets longer the bigger your data set gets. So here I'd add these numbers up: 32, 34, 34, 41, 44. Add those up. We got 185. That's my data set right there. So 185. But I need to divide that by 5. So I actually get 37 for my mean. So 185 divided by 5 will give me 37. So 37 is the mean. That's the value I'm going to use to get my deviations. So again, each deviation, I'm going to take the value, like 32. I'm going to subtract this mean. So I'm going to subtract 37. I'm going to do 34 minus 37. 34 again minus 37. 41 minus 37. And 44 minus 37. Then I subtract, watch the sign. So 32 minus 37 would be a negative 5. 34 minus 37 is a negative 3. 34 minus 37 is still negative 3. 41 minus 37, now I'm going to get positive because the bigger number was first. So I'm going to get positive 4. And 44 minus 37, that's going to be a positive 7. You can check and see if you're doing it right. If you add these numbers and you get 0. So like we do negative 5, negative 3 is negative 8, negative 3 is negative 11, plus 4 is negative 7, plus 7 is 0. So this should actually add up to 0. That's why we have to do the next step, which is deviations squared. So I'm just going to take each one of these numbers and I'm going to square them. Negative 5, you square it, you get positive 25. Remember, anytime you square a negative, it becomes positive. Negative 3 squared becomes positive 9. Same thing for the negative 3, and then a positive 9. 4 squared is 16, and 7 squared is 49. Now we sum those. We add those up. We get a total for the deviation squared. So I'll use my calculator to make sure I don't mess up. So 25 plus 9 plus 9 plus 16 plus 49. And I get 108. That is the sum of all the squared deviations. Next, I want to divide by n minus 1. Well, notice n is 5, right? We already counted the number of values. We said there's 5. So n minus 1 is 4. So I'm going to take 108 and I'm going to divide it by 4. So we always take this and divide by n minus 1. So we're divide by 4. So 108 divided by 4. Just hit the divide key and then 4, and then I got 27. Last step, after you divide, you have to square root that answer. Don't forget to square root because we just squared everything. We can't leave it squared. We've got to go back and undo that. So we square root everything. So I take a second. Square root of 27. So I just typed in square root of 27 on there. And I get 5.196. So 5.196. And that is our standard deviation. So we took all the distances between the values and the mean, and we averaged those out to get kind of an average distance. And some of them are not nearly that far from the mean. Like the mean is 37. These 34s are pretty close to that. But we've got values like 32 that's whole 5 away, 44 that's 7 away. And this is just an average of those distances. So we can kind of get a measure of like how spread out this data is. The closer the values are all to the mean, the smaller your standard deviation is going to be. The more spread out they are, the bigger the standard deviation. So that's what standard deviation does. It's a measure of how spread out your numbers are. And it's a process to get. You got to think, okay, I need to find standard deviation. First, I need the mean, because you use that to find the deviations. You subtract the mean from each number, that's your deviations. Square those to make them all positive. So once you got them all squared, add them all up, get your total of your squares, because you need to add them up to divide, so that's how you average. But when you divide, don't forget to subtract 1 first. Use a smaller number, so divide by n minus 1. Divide by 4, and then the last thing is to undo that square. So we'll do it one more time. You guys really get the idea of doing this standard deviation. Be ready. You'll definitely have to do this at least once on the test. So be ready to find standard deviation for a set of numbers. One cool thing about standard deviation, it's actually really, really powerful. It really helps you understand and spread your data. We'll use it a lot next week. Or in the next section in 6C, I won't make you find it because we'll give it to you. You'll see how you can use it for more information. It's just a powerful tool. It's actually, in general, values in your data set are going to lie within 2 standard deviations. Like the vast majority of your data will lie within 2 standard deviations. So if you just pick a number at random from a data set, you should expect to be within 2 standard deviations of the mean. That's a pretty powerful thing. It is extremely, extremely rare for any value to be more than 3 standard deviations from the mean. If you went and took a standardized test and you were more than 3 standard deviations from the mean, they probably think that either you cheated or like something really bad happened with your test results. It would just be very unlikely, and they'd probably research and find out what happened if that happened, because that's a big deal if you're more than 3 standard deviations from the mean. Most people are going to be within 1 or 2 standard deviations of the mean on a standardized test. All right, let's find the standard deviation for this set of data. Again, the first thing you have to do is find the mean. So before we can do anything else, let's figure out what the mean is. I'm going to add these all up and divide by how many there are. So I've got, there you go, 15 plus 9 plus 14 plus 17 plus 18. 5 values, add them up, I get 73, by 5 values, so I get 14.6. The mean is 14.6. Add those up, divide by 5. Now to find the deviations, again, the first thing we do to find deviations is I'm going to subtract these numbers. I'm going to subtract 14.6 from them. You'll notice I'm not putting them in order. You don't need to be in order for finding standard deviation, so you don't have to. For something like this, I can just go ahead and do them as they are. So 15 minus 14.6, which is 0.4. 9 minus 14.6, which is actually negative 5.6. I got 14 minus 14.6, which is negative 0.6. 17 minus 14.6, which is 2.4. And 18 minus 14.6, which is 3.4. If I add these up, if I did it right, they should add up to 0. So I could do it 2.4 plus 3.4 is 5.8 plus 0.4 is 6.2. If I add these two up, I should get negative 6.2. 5.6 plus 0.6 is negative 6.2. So yeah, if I check that, if I add this all up, I get 0. You can double check it with the calculator. Then I want to find my deviation squared. This one's going to be a little bit more of a pain because I have to square all these decimal numbers. That's the nice thing about having a calculator. I just type it in, 0.4, and I do my squaring button. So the X squared button right down here. It's easy to square them. Do 0.4 squared and I get 0.16. 0.16. I get negative 5.6 squared. Now, if you're not careful with this and you're doing negatives like this, you'll see you get a negative answer. That's because you didn't type it in correctly. So I get this all the time where people do standard deviation, they get negative, and they go, well, the calculator said it's negative 31.36. No, you're supposed to be typing negative 5.6 in parentheses and then squaring it. Because the calculator, when you put a square like this with just the no parentheses, it's just squaring the number and it's ignoring the negative. If you want to square everything, including the negative, you have to put it in parentheses. Personally, I just type it in without the negative because I know that anytime you square a number, you get a positive. So I'm just going to type 0.6 squared. I'm not going to worry about typing a negative because the whole point of doing the squaring part of this in the calculator is because it gets rid of the negatives. It makes them positive. So I know that this should just be squared and become a positive, 0.36. If I do 2.4 squared, 2.4 squared gives me 5.76. And 3.4 squared gives me 11.56. And then we're just going to add those all up. So let's take those numbers, add them up. So I got 0.16 plus 31.36 plus 0.36 plus 5.76 plus 11.56. There you go. Adding it up, we get 49.2. That is our sum or total of our deviations squared. average, when you divide by number of values, but not by n, we divide by n minus 1. So in this case, there's 5 for n again. So we're going to divide by 4. So we're actually going to take this 49.2 and divide it by 4. So we always divide by 1 less than the number of values when we do standard deviation. That's a little trick for standard deviation. Divide by 1 less. So I get 12.3. Last thing we have to do is remember, this is a squared value. Because we squared all these things, we have to go back and square root it. So I have to square root that 12.3 to get the final answer. So the last thing we have to do is do this. We have to square root 12.3, and we get 3.5. I'd say round to 1, or maybe you put 0.7, I guess. Depends on how many spots. I guess I've been doing 3 decimal spots on the rest. I'll do 3 on this one. 507. My math will tell you if they want you to run 2 decimal spots, you just run the 0.51. Or if they just want 1 decimal spot, you just put 3.5. That's a major standard deviation. Now, this data set's a totally different data set than what we had before. Here, these are values in the teens. These are values in the 30s and 40s. But we can still now compare them in their spread, at least. We can see these numbers are not very spread out. They're only 3.5 for their spread, versus these numbers had a spread of 5.196. They have a bit more spread. And if you go to even like, values that are more spread out, you get a larger spread. It doesn't necessarily have to be bigger or smaller numbers. Yeah, these are smaller. That's not why they have the smaller spread. The spread is how much distance there is from like top to the bottom, the spread of the data set. So that's what standard deviation measures. Standard deviation is a little bit perturbed by outliers. So you saw earlier range, outliers could really mess it up. Standard deviation still is a little bit messed up by outliers, but it's not as bad as range. Because it used all the numbers and not just the top and the bottom, it's not as susceptible. It's more like mean, where mean gets messed up by standard deviation, by outliers. The standard deviation is just not quite as susceptible. But it's still kind of the best one to use. We don't really have a lot better measures for standard deviation, so that's the one we will use most of the time. If you get into higher level statistics, if you took like a couple college level statistics course, after the first one, you get into other measures for variation that are maybe a little bit better, but they're also more technical, a little harder to work with. So that's it for us in this section. We're done with working just finding the variation. Now we have a way to measure that with the standard deviation, with range, and with the 5-number summary. So we actually have a couple different ways to measure it. Range, again, is not that great because it's so messed up by the outliers. 5-number summary just takes too many numbers, so we don't use it as often. Standard deviation is kind of the next one because it just uses one number and it's not as susceptible to outliers. So I'll see you on the next set.